The recording has started.
Okay. Yeah.
Okay, so can we start?
Yeah, I think this one can be quiet. I'll close the doors.
Okay.
Sure. It's very quiet.
Yeah,
okay. The volume can be.
Okay, good afternoon, everyone. Welcome to the third edition of the Week of Webinars today. So, the Week of Webinars is the final week of Summer of Weather Code from ECMWF. And for those who don't know what ECMWF is, we are the European Center of Medium Range Weather Forecast, and we are both a research institute and a numerical weather prediction center. And we provide numerical weather predictions to national weather services on an operational basis, 24 hours on a 7 days. And so we have the Summer of Weather Code is a program. It ran for the first time this summer, and it's a program where we invite startups, developers, students, scientists to come and work with us for during the summer on innovative and weather-related code. And so, this was the first year we ran this program, and since May, 5 teams teamed up with ECMWF mentors to work on 5 different challenges. And so today we will present the outcomes of one project this year, and Anirudah Bose, he worked on the migration of a calibration software which is used here at ECMWF. And he also developed for the software specifically a GUI for it, that it's easier to use. And so the mentors at ECMWF were Tim Hewson to the left and Fatima Piloscu to the right. And I will hand over to Fatima, who will explain more what the software is doing and why this calibration software is so important. And so the webinar structure will be that Fatima will present the motivation behind the challenge. Anirudah will present how he developed the software and the migration to Python. And then afterwards, if you have questions, it's open for everyone to ask a question. So then now I hand over to Fatima.
Thank you. So I will start sharing the presentation. How do I do that? Yeah, share screen, right?
You need to put it in.
Start sharing. Yeah. So hello to everyone. Here we are for the third challenge, migration to Python of ecPoint-PyCal and creation of the GUI for the calibration system. We have been working with Anirudah Bose from Paris, and we have been developing with team, helping him during the whole process. So,
Right.
Sorry.
I think you have to take the mouse.
Yeah, probably.
Don't you know?
Okay. So the presentation today is going to be organized in 3 parts. The first one is giving you a bit of background on what the post-processing system ecPoint is and what the calibration software does within this project. The second part will be entirely to Anirudah to explain how he migrated the software into Python and how he managed to create a really interactive GUI that is the most powerful thing of the calibration software at the moment. And the third part is going to be entirely from Tim to talk about the uses that we can do of ecPoint-PyCal at ECMWF. So I just start talking about a bit of the project. ecPoint is a statistical post-processing system that we use to produce probabilistic forecasts at point scale from model forecasts. And the ecPoint-Cal is the calibration software that we use within ecPoint to produce this point scale forecast. So just to give you an idea of what the post-processing system does. If we look at this picture, we can see this is a rainfall example. We see in the grid, these are the model forecasts that are produced, one value, in this case of rainfall forecast for each grid box. And behind that, you can see a map which consists in the radar-derived rainfall totals. And you can see that within the grid boxes, there are different values of point rainfall values. In different cases, they can be, for example, like in the orange, brownish grid box, the values can be more uniform, vary between like 0.5 to 1.5 millimeters. But in other cases, we have, like for example, in the blue grid box, we can have much more variation of the rainfall values within each grid box. For example, in that case, we have values that go up even up to 20, 28 millimeters. So in this case, the grid boxes were representing the ECMWF ensemble forecast system, which are 18 kilometers. What we want to do is to post-process the model forecast to obtain a distribution of point values for rainfall forecast within each model grid box. And to do that, we need some information for the calibration. We need observations of the variable that we want to deal with. And for example, in our case, is 12-hourly total precipitation. And then we need the model forecast of the observed variable, which from now on we will call them predictants. So in our case, 12-hourly model data, model precipitation forecast, sorry. So how do we do this post-processing? What we do is basically compute an error metric for the model forecast versus the observation. And because we are talking about rainfall forecast in our example, which is an accumulated variable, we compute what we call the forecast error ratio, which is just basically the difference between the observation and the calibration software, the difference between the observation and the calibration and the forecast used for the calibration, which is a short-range forecast. In other cases, for example, if we were using temperature, because it's an instantaneous variable, we will be computing the forecast error, which is just basically the difference between observation and forecast. What we see in the picture here is basically where we compute the forecast error ratio for all the observations that we have available in our data set, we can display the frequency, with which frequency the model forecast overestimated, underestimated the observations, or when were they reliable. And with that, we can study the behavior of the rainfall forecast against the observations. So what we want to do now is introduce a bit more complexity to the system. And to do that, we want to consider some other model variables that we will call predictors that will help us to define a certain grid box weather types. And for each weather type, we want to analyze which is the relationship between observations and predictants, and that can, in certain cases, vary significantly. The weather types are basically defined by identifying breakpoints for each predictor. And a very useful way to visualize the weather type is using a decision tree. So here, you see an example of a decision tree where we have the distribution on the top, the distribution of all our cases. And then as soon as we go down in the different levels of the decision tree, we can see, for example, the first division relates to the cases we are considering, for example, mainly large scale, mainly convective precipitation, and how already at the first level we can see differences, big differences in the relationship between model forecasts and observations. And then this behavior, this relationship can vary further by considering other predictors like total precipitation, wind speeds, etc. So the project started in 2016. Since then, we have been developing the calibration software that originally was called ecPoint-Cal, and the post-processing system, which is ecPoint. And then since last year, we have been using, for the first time, the calibration software to produce, for the first time, the post-processed ECMWF ensemble rainfall forecast that we call ecPoint rainfall. And since this year, we are producing these forecasts on daily basis in semi-operational mode. But do we want to stop here? Absolutely not, of course. The applications of ecPoint and the calibration software are several. And for that, team later on we will give you a talk on that. But to keep developing the ecPoint and ecPoint calibration, we need the right tools, which means in the first case, having a calibration software that can help us to be more dynamic. So the limitations of the previous version of the calibration software are quite a few. So, for example, we have been using two software packages, MedView and MATLAB, within the calibration software, which doesn't allow a seamless workflow. Even if, for example, MedView is freely available, for people that don't know it, that means that represents a learning curve to actually start using it. And MATLAB, even if it's a bit more spread, the user of MATLAB is a bit more spread, is not freely available. Then we have developed the calibration software only for rainfall because that's the parameter we started. But for example, we would like to apply the calibration to other variables like temperature, wind. So at the moment, we don't have this flexibility. Then we use grid files for the forecast because this is what we use here at ECMWF. However, netCDF is really widely used format, so we would like to have this software. We would encourage people in other places to use it and give the possibility to them, if they have netCDF, to use it anyway. The computations that can be done within the calibration software are predefined. And for that, I mean very simple computations, for example, computing accumulated fields, compute weighted averages, compute the module of vectors. And at the moment, we can compute only, we can do only computations that are strictly related to rainfall. So we want to, so if we want to add or remove other computations, we need to access the source code. Then we have no dynamic visualization of the decision tree. The mapping functions are saved into files, and then the user has to manually build the decision tree. And after 3 years working on that, I can tell you that that's a really boring task. And as well, it's quite long. It takes a long time to do it. Then as well, there is not the possibility of dynamic interactions between when you look at the decision tree. And that's a really important thing because that's what actually allowed us to study the behavior of the forecast versus observations for different weather types. So this is one of the aspects, for example, that we really pushed in the GUI. The things that we wanted to have a GUI and we wanted to have it implemented there. And then we have, in the previous version, we have the maintenance of configuration files in ASCII format, which are error-prone and not very user-friendly. So another aspect, that's another aspect that has been improved in the GUI. So I hope this is all clear. Now I will ask Anirudah to start his presentation. So should we just stop the sharing?
Stop sharing.
Yes.
Yeah.
All right. I hope I'm audible. Thank you, Fatma, for the introduction and walking us through the fundamentals. And good evening to everyone at ECMWF and to others who are joining us from joining the live webcast. So I'll start by doing a live demo of the new ecPoint-PyCal software suite that we developed over the summer, and I'll be explaining some of the features and how things are working behind the scenes along the way. So I'll share my screen. So we can launch the GUI using a command since I'm developing it locally, so I'm doing npm start, but if you have it installed locally, you can just use the name of the software, which is ecPoint-PyCal, and it will launch the GUI. So as soon as we open the GUI, we are presented with this screen where we are asked to choose one of two options. Either you can start from scratch, or you can load a pre-computed ASCII file. Now I would first like to show you what happens if you start from scratch, and later on I'll present you what happens if you load something from disk. So when I start from scratch, the first thing the user sees is this page where he or she is supposed to enter the input parameters that will be later used in different computations. So we start by selecting the predictant, which is so you have to select the model forecast data for the observed variable. I happen to have these things on my disk, so I'll choose them. So for as a predictant, I'm choosing total precipitation. Next, I'm supposed to choose the type of the predictant, which could be either instantaneous or accumulated. In our case, this is an accumulated variable, but if you would have chosen something like temperature, that's an instantaneous variable, and you're supposed to click on the instantaneous radio button. As you can see, the UI suggests the user that the predictant error that is computed if you choose an instantaneous variable is called forecast error. This is the same thing that Fatima was talking about in her introduction. In our case, total precipitation is accumulated, so I'll choose accumulated. When you choose accumulated as a type, you must also provide the accumulation in hours. Valid values are 6 hours, 12 hours, or 24 hours. So, but if I try to enter something garbage, the UI will shout at us. For now, let's just enter 12. And then finally, we are also asked to enter a minimum value for preventing division by 0. This is just a minor technicality that is associated with the way observations are recorded. So in our case, I'll just choose 1, and it needs to conform with the kind of units that you choose later in computations. But for now, let's just say it's 1. So once you have chosen the predictant, you must also select the observations. So I click on browse, navigate to my database, and select the total precipitation observations. This is because I'm using total precipitation as my predictant, so it's only logical to use total precipitation observations. The third thing is to choose the predictors. So these are the inputs to our different computations that will be later used for post-processing. I click on browse, I go to the location where my predictors are stored. It happens to be in this directory, and I say OK. And you can see that the UI now says that it gives us the list of predictors that's available in the disk, and we'll be able to use them later. Now, you may have predictor data as in GRIB format or in netcdf format. I'll just choose GRIB because that's what I have right now on my disk. Moving on to the next section, we define the parameters for that is going to be used later in the computations. We would like to limit the whole computation between a time window. For example, in my disk, I have data from June 2015. So I'll just select those dates in my date pickup. Let's say we start from 1st June and we end at something like 3rd June or 4th June. Let's say 3rd June. The next two fields are again, they are technicalities. Computer, we have a field for specifying limit or ignoring data, save it to 2 hours. The average lead time must be encrypted, so in hours. So actual value is 1. We'll increment and pay attention to this. Is that we are asked to select an output file name for storing the results. So the results of the computation are stored in an ASCII file, and whatever location we specify in this dialog, that's where we'll find the final output. So let's say ECMWF.ASCII. It's supposed to have an ASCII extension. So once the user has completed all the different sections, you'll see that in the top nav bar, I now have the computations step activated. So I can move to the next step, and this is where we define the various computations. So in the previous legacy software that was written using MATLAB and MedView, the computations done by the MedView code was hard-coded, which means it doesn't matter what are the kind of predictors you have or what you want to do. You must go through the same, you must execute the same computation every time because it's hard-coded in the code base. In our case, we try to improve upon this. Right now, this UI allows the user to define computations. So computation could be something like, let's call it TP, and it's an accumulated total precipitation. It is an accumulated field, but it can be something else like ratio field, instantaneous field, maximum minimum field, average, weighted average, so on. So each of these fields has a corresponding definition and method defined in Python. So whenever we choose one of these field types, the corresponding computation is run. So we say it's an accumulated field. We also provide an input variable. So it's, as you can guess, you're supposed to enter total precipitation. Now see that, note that whatever input variables are available in the list is coming from the list of predictors that we already have, that we selected in the previous step. So selected total precipitation. And in the next column, we have another feature that allows you to scale your computed values or up or down. So you can multiply, divide by a constant factor. And the reason why someone would want to do that is for adjusting units. For example, in the database, the grep files that we have, the values are in meters, and normally in logical computations it's much more convenient to deal with millimeters. So to convert meters to millimeters, I can multiply by 1,000. So that's why this scaling factor is for. Yeah, that's it. So in the same way, we can add something like let's add U700. So U700 is another weighted average field that we commonly use, and the input is going to be U700. So this is the predictor that we already had. I have nothing to multiply or divide, so I leave the fields as it is. I do the same for V700. So it's also a weighted average field. And by the way, the weights are the weights and the corresponding operation, like I said, have been defined in the Python process. Like V700 as the input variable, and that's it. So the reason why I added U700, V700 was that I wanted. So I have the horizontal component of the wind speed and the vertical component. What I want to do is get a root mean square. So I create a new computation called WSPD, which is nothing but wind speed. And it's a vector module. The field is a vector module, which is basically computing root mean square. And note that the input variable in this case is U700 and V700 computed in the previous steps. So not only can you use predictors as input variables, but you can also use computed fields as inputs to some other computed field. So this makes the whole process much more flexible. And as you can guess, once you have the wind speed, there is no reason why we should process the U700 and V700. For this reason, we have a separate column called post process, and it's a checkbox where if you uncheck it, it will be just omitted from the final ASCII file. So we won't be post processing these fields. So that's it. Now that's how the computations framework is working. Once you are satisfied with your computations, you can move to the next step, which is processing. So in this step, as the name suggests, we are going to launch the computations defined in the previous step, and we are going to generate the ASCII file. So when I click on launch computation, you're going to see the live logs from the Python process in real time, and you will be able to see if you wait a little while, then you'll be able to see an ASCII file generated in the location that I input in the previous steps with the calculated data. Now I'm not going to bore you with ask you to stare at the screen for several minutes or hours, so I'll just stop this process, and I'll show you how the process is if you already have a pre-computed ASCII file. So I already finished the computation before, so I have the file with me. So I open the ecPoint-PyCal software again, and we see the same welcome screen that we saw before, but now instead of starting from scratch, we click on load a pre-computed ASCII file. table. So now it is asking us for the path, the ASCII file. I have it stored in my computer, so I choose it. So so what you are seeing now is that the software is reading the ASCII file, and it is figuring out what's inside it. So there are several metadata that's encoded in the ASCII file. And at this point, I would like to show you how this ASCII file looks like. So I move to my screen. I'm not sure if this is readable, but this is the ASCII file that I just loaded, and it has all the parameters that we defined. It has the information about the predictant, and it has also information about what are the post-process computations that we want to use. So in this case, we have 5 computations: total precipitation, convective precipitation ratio, wind speed, convective available potential energy, and solar radiation. So we believe that these are the fields that can affect total precipitation, and now we'll use the software to post-process and verify our hypothesis. I switch back to the software, and so now the last step. So we are at the last step, which is constructing the decision tree, and as the name suggests, it's a tree, and every level of the tree is actually a computed variable with that's going to have several breaking points that Fatma was talking about in her introduction, and the section that you see right at the first, it's like you see 5 different computations. They are actually the levels. It represents the order in which the levels will appear in the decision tree. And maybe the order that is presented by default from the ASCII file is not what you want. So the user can rearrange these levels to his or her liking by just clicking on the computation and just doing a drag and drop. So I can just choose it, choose any location. I think let's put CPR as at the top of the level, top of the decision tree. And as soon as I did that, maybe you notice that in the table below, you can see the different columns getting rearranged. So this is also the order in which we will be entering the breakpoints, threshold breakpoints. So once you can rearrange as much as you want, but once you are satisfied with the order, you can start inputting the threshold breakpoints. So for the sample data that I input, I just happen to know the breakpoint values that's going to yield some meaningful graphs. So I'll just input them. Previously, we used to maintain in the legacy software, we used to maintain a spreadsheet having these breakpoints. So you have to maintain the spreadsheet as an external file, then the program was supposed to read from that, and it was clunky. I think a unique value provided by the GUI is that you have the same familiar interface of a spreadsheet, and you can use this interface to input the breaking points. So what we do here, I just input the different threshold splits. So I put here -infinity. So INF means infinity. So I keep on entering some values. Um, so that's it. That's how you enter these threshold breakpoints, and notice that this matrix is sparse, and it is sparse for a good reason. The reason is that if you so you'll see after we can ask the Python process to generate the full matrix for us, but even with small additions, you can have a really huge um, matrix, decision tree matrix, and it's next to impossible to ask a human or to rely on a human to input all the values correctly. So it's just currently the way we are defining the threshold splits, and we can ask the backend to give us the full version. So I click on generate full decision tree, and it creates this matrix. So in this matrix, each row is a unique weather type, and all the columns are actually they denote the levels in the decision tree. Internally, the post-processing that we do is using this matrix for generating the graphs and evaluating the decision tree, but it's not that intuitive. So because a decision tree must look like a tree to begin with. So also as a part of this project, I try to visualize this tree like a real tree, and this looks like. It kind of resembles the same kind of graph that Fatima was showing, having a tree with multiple graphs. So this one it's actually inside a canvas, and you can play with the graph. You can click on nodes to expand or collapse some levels. You might want to do that because in this case, we don't have a lot of predictors or a lot of breaking points, but we might as well have certain cases where the tree is so large that you cannot analyze or verify the results entirely. So it makes sense to just focus on the part that we care about. Yeah, so this clicking on these nodes lets you do that. So in this decision tree, each path that leads to the leaf is actually a weather type. And if you follow each of these paths, it means you are evaluating the decision tree. So as you can guess, the leaves, when you reach the leaf nodes, the decision tree is completely evaluated, and that's where you get the graphs. So I'll just click on one of these leaf nodes to show you sample graph. Yeah, so it's not colorful like the one Fatima showed, but yeah, this is it. That is the end of my demo. I'll move on to the slides, to the rest of my slides. Yeah. Sorry. I hope my screen is being shared. So what we just saw was a demo of the different features that we had. To sum up, our software ecPoint-PyCal supports multiple data loaders for different file formats. So we have GeoPoints, Grib, NetCDF, ASCII files, and so on. We have seamless integration between the various components. So notably, the computational component, which was formerly written using MedView, and the post-processing component formerly written using MATLAB. So now you don't have to manage two softwares. You just have one software suite. We have a dynamic computations framework. So this allows you to have arbitrarily complex or simple computations based on the kind of predictors that you have. We are also supporting loading of pre-computed ASCII files. So this means that maybe your colleague will perform the computation, store the results in an ASCII file, and share it with you. So you can perform the next steps, that is post-processing, which doesn't require predictors or predictant files or observations. All you need is this ASCII file. So it's really helpful. We also saw that how easy it is to edit the threshold breakpoints in the GUI. Instead of maintaining an external spreadsheet, now you just have the same interface, but on the GUI. We also saw the amazing decision tree visualization. So, when Fatma said that it is a really boring job to assemble all the graphs together in a tree, so now she won't have to do it anymore. So it's also much easier to figure out what's going on, to follow the paths in the decision tree, which looking at a matrix is kind of impossible. And finally, something not related to the software itself, but we have a universal Linux packaging using something called Snapcraft. So what this allows us to do is, with one command, have this software installed on any Linux-based operating system. So this is really great. If you have Snapcraft, then start using it right away. And this morning, we also got support for Docker, which was contributed by Carlos from ECMWF. Thanks a lot to him. This is a similar technology that allows you to run the GUI without having to go through the installation steps. So it's package once and run anywhere you want. I'll explain a little bit about the tech stack. Our tech stack is divided into two main components actually. One is the Electron server, which is the application server for rendering the UI that we just saw, and a Python server that is powered by Flask. So Electron is it's an open source cross-platform framework that's used to create native apps using JavaScript. It's running a runtime in behind the scenes that is allowing us to write apps in JS. So I have developed the UI using React and Redux. And the reason why I chose these technologies is that it allowed me to develop the UI very rapidly and iterate over ideas much faster. Plus, the interactive experience is something React is particularly strong at. We also have a Python multiprocessing pool that you can see in the tech stack picture. So this is just to parallelize some of the more heavy-duty computations that's happening, notably related to grip. Okay, that's it for tech stack. I'll talk about some of the next steps that we have planned for this software. So the first point is definitely improve the decision tree algorithm, because right now we are inputting the breaking points manually, and we would like the algorithm to figure it out by itself. And secondly, we would like to reduce the cost of computing various fields. So right now it's if the performance is X, we can we can greatly increase the performance by many times if we can get a fix that we have suggested to EC codes upstream. So EC codes is the underlying package that we're using for manipulating grip files, and due to a missing feature, it is affecting the performance greatly. But good thing is that we have created a Jira ticket and the developers have taken cognizance of the issue. And once it is fixed, we can hope that the UI will be much faster. Okay, so this is where we have hosted our code. I'll just quickly go to the repository and show you. So it's hosted on GitHub. Feel free to fork it and make any contributions if you want, or try the software out and create new issues. There are installation instructions. So if you're using Snap, then it's just one line. If you are more adventurous, feel free to try out the manual installation steps. I do not recommend. Okay. Finally, okay. So I wanted to talk about my ECMWF ESOWC experience, and I think this GIF pretty much sums up how I feel at this point after completing the program. So I really thank my mentors Fatima and one second. Okay. I would like to thank Fatima and Tim for the guidance and the technical help that they gave me right from the very beginning at all steps, especially because I had negligible, zero knowledge in meteorological things before starting the program. I think I've picked a few things along the way. Thanks for that. And secondly, I would like to congratulate Julia for success of the Summer of Weather Code program, and thank ECMWF for the amazing opportunity that they gave me. Okay, that's it from my side, but I think Jim has some closing remarks to share with you, so I hand it over to him. Thank you.
Okay, thank you very much, Anirudah. Thank you to you for doing such a fabulous job with the coding and so forth, and being extremely patient with us when we didn't quite deliver to you the things we said we would on time. So we appreciate that. We did our best, but it wasn't always quite as good as it could have been. But anyway, so I'll just do a little run through of why this is important to ECMWF and how it can be used. So this is part of a long-term project which is we entered a competition many years ago, and this is just a few sort of slides of things or pictures of things that have been part of this project along the way, but I won't talk about all of those now. We don't have time. Okay, so how can this help ECMWF now and in the future? Well, the point about this is that ecPoint-PyCal is part of a non-local calibration technique, and the benefits of that non-local calibration technique, which we kind of invented here, are many. From a modeling point of view, you don't need to do lots of model reruns to be able to calibrate your model. By having this non-local technique, it's equivalent to using hundreds or thousands of years of observations in the more classical calibration methods, and it also gives you concrete insights into physics-related model problems, as we'll see, such as biases. And before you can fix them in the model, you can also correct for them in the model product. So those are the benefits of non-local calibration. And so the software basically allows us to exploit those benefits in the following ways. So the first benefit, which I will not say a lot about, it's a big talk for another day, is that the forecasts that come out of the ECMWF model are much improved by doing the post-processing, which is based on the output of calibration, essentially. That includes extremes, extreme rainfall, etc. And so we have lots of applications, flash flooding, etc. At the moment, it's just for rainfall, but in principle, by using ecPoint-PyCal, etc., we can address other parameters as well. Second topic, it's a flexible user-driven tool for conditional verification, which is a kind of growth area in the world of verification of models. The decision tree approach allows us to analyze quickly how different factors affect the model performance, how they affect the model biases, how they affect subgrid variability. You can do lots of parameters. The factors can be anything. You could put in population density, you could put in altitude of orography, you could put in vorticity, you could put in any model or other parameter you want. And then when you get the results out, that helps us to the research activity of ECMWF to target the causes of model error. And then a final use, which I won't talk about today, is just to highlight that I think we also have in here a potential to develop an advanced probabilistic reanalysis tool for point values. We could take ERA5 as input, and then we could get, instead of getting grid box averages for 32 kilometer grid boxes, which is what the ERA5 provides, we can get reliable, in the statistical sense, probabilistic representation for every grid box of the point values in those grid boxes, which conceivably could give a kind of world-beating reanalysis product of, for example, rainfall for any data in the past, and this will potentially fill gaps in the climatological observations that we have. Okay. So I'm going to focus now on the conditional verification. That's the only thing I'm going to talk about today. Just give you a couple of examples. 2-meter temperatures. This is a simple example using a histogram approach related to the blue histogram that Anirudah showed a little while ago. And secondly, rainfall, sort of serendipitous case study which arose when we were looking at some of the output from the point rainfall product. Okay, so if you think in terms of model error, there are different sources of model error, different lead times on the x-axis. You have bias on the grid scale, you have representativity, and you have random error. So in this project, we're addressing the dark red and the green aspects of this. And so using conditional verification, we want to basically work out how big the green and dark red bars are and how they vary in different situations. Different situations means these different controlling variables. And so that can then tell you what the error sources are for the model output. Okay, so in a simple histogram approach, the user sets up the controlling variables in ecPoint-PyCal, model or other, the ones they think are relevant. They then create threshold-based subsets for those variables using the decision tree. Then they look at the error metrics for those different subsets, such as comparing all cases with a particular subset. And then in the module 1, which is kind of is not developed yet, we can do a more sophisticated approach using Kolmogorov-Smirnov tests to recommend multiple breakpoints rather than selecting them yourself as the user in an interactive way. Okay, so let's say we're talking about 2-meter temperatures. Let's say we have extreme conditions, deep snow, light winds, clear skies, nighttime conditions. That might be part of your decision tree. All those sort of factors are satisfied. Then you look at lots of cases over the world, over a month or a year or whatever, and then you plot the, in this case, not the forecast error ratio, but the error in different bins. So these bins on the x-axis are bins of the error magnitude when you compare the model forecast with the observed 2-meter temperature short-range forecast. And if you look at the extreme cases, that's shown by the red ones. Those are the ones which satisfy those little ticks, the deep snow, light winds, etc. And you can see there's a much broader range of errors in that scenario, whereas in the all cases over the whole world for this period, the errors are much more confined. So what this is telling you that those extreme conditions lead to bigger errors overall in the 2-meter temperature forecast. Not only do they lead to bigger errors, on average, they also lead to a bigger bias. So this is forecasting temperatures too low, which means that the orange is shifted across to the left rather than the right of this. And that's the sort of thing that we would like to address with changes to the model. So in this vein, ECMWF should investigate 2 metre temperatures over snow, because that's where our biggest errors occur, etc., clear skies, etc. We're actively doing this. Then a future question you might want to ask is that we see these errors generally, but we know that over Finland, based on their feedback, the errors are somewhat different over Finland. Then you think to yourself, okay, what characteristics of Finland make the errors different there? Maybe it's the fact they have a lot of lakes, for example. You can put that type of parameter into your ecPoint-PyCal and investigate the influence of lakes on the errors. Okay, so that's one example. My second example is rainfall. This is the same plot we saw before, just that the green bars are a bit bigger. That means that the representativity for rainfall, as Fatima showed with the radar picture at the beginning, is the representativity error tends to be bigger. Okay, but not only that, the biases for the different weather types, these are like the decision tree leaves. So this is from our kind of operational point rainfall system. This shows you that the biases that are intrinsic to each of those different weather types, which are the decision tree leaves, are rather different. So in the context of the bars that we saw on the previous plot, if there's no dark red bar, then that means the bias is 1 in this context. So that's where these weather types give you a bias of 1, where they coincide with that red line. But anything which is over that is under prediction. Anything which is below that is over prediction. And so clearly, in certain situations, the dark red bars are very large. Okay, and so this then spurs us on to thinking about how can we use a case study, raw versus post-process forecast, to help with model development. So you think about a forecast for a given location on a given day. We look at the raw point rainfall versus the ensemble rainfall. We look at the differences, ask if they're large, and then if that is the case, we see what happened. Was the point rainfall forecast better? If it was better, then maybe it's latched onto something. And then you ask the question, how do the distribution differences relate to the main weather types identified? What is special about these weather types? Then you can look at where the calibration data came from, etc., etc. And then this leads you down the route of addressing what physical mechanisms might be causing the model to go wrong in terms of the change bias characteristics in that particular area, that particular regime. So here we have an example which we saw, and I was quite surprised when I saw it. I thought something's going wrong, but it wasn't going wrong. This was just an illustration of the applications of this. Here we have a point rainfall forecast in blue and the raw ensemble in red. 12-hour precipitation, it's cumulative distribution function. So the further it is over to the right, the larger the amounts of rain that are shown overall in this probabilistic regime. The further to the left it is the dry read. So you can see from this that the point rainfall is showing overall much drier outcomes are more likely than the raw ensemble, which means that there is a bias correction. Okay, and then we can look at the weather types that the point rainfall was dealing with here, how they relate to that the multi-bar chart that I showed a moment ago. What we saw, mostly we had convective precipitation, large rainfall totals forecast, moderate winds, convective potential energy was modest, minimal insolation. And in fact, the reduction of the rainfall, we spoke to Norwegian forecasters about that. That's exactly what they would expect. They would expect that the model would overdo the rainfall in this particular type of synoptic situation. And in the end, the observations that we obtained from some people in Bergen, radar-derived totals and observed totals, were much better matched with the point rainfall forecast than the raw ensemble. So this suggests, it's only one case, but it suggests that the model is actually, so the post-processing is doing the right job in reducing the amount of rainfall in this situation by quite a lot. Okay, and then you can ask the question, where did the calibration information come from to improve the Norway rainfall forecast? Then you can look back to your calibration procedures. This came from would have come from ecPoint-PyCal, and you can see that most of those locations which satisfied those particular weather types are over mountainous areas, such in the northwest of the US, the UK, southwest of New Zealand. This is just the frequency of when the observations were used in this context. Okay, so what that means is that probably these scenarios generally occur in mountainous areas. And in fact, this is the position of those weather types on the graph I showed before. So clearly, we're expecting a lot of over prediction in that scenario. There are physical explanations for this. We're running out of time, so I don't want to go into that. But there are physical explanations which will explain why the model is overdoing the rainfall here. But just to highlight that using ecPoint-PyCal, we can further focus on those mountainous areas to try and refine the actual physical explanation a little bit more. And then modelling effort in the long term could hopefully address this model weakness in due course. So there's a whole chain here for using ecPoint-PyCal within the framework of numerical weather prediction. We have conditional verification, we have understanding, we have calibration, we have model development, and we can move backwards and forwards down this chain. In the shorter term, the calibration corrects the errors, and then in the longer term, by addressing the problems with the model, we can actually make the model better. So that's why this is very, very valuable to ECMWF. Thank you for this.
Okay, so then we would open the floor for any questions. Are there questions either like content-wise for why the calibration software is used, or like on the technical implementation of the software? Okay, so there is one question, Anirudah, when you define the folder where predictors are stored, all the available variables are selected. Is it possible to remove some predictors from the default list or load variables from different folders?
Can you repeat your question again? Your first part I couldn't.
It's on the chat. You can see the chat.
Yeah.
Okay, 1 second. One question for you. When you define the folder with predictors are stored, all available variables are selected, is it possible to remove? So actually, you don't need to remove anything. By default, you have all the predictors available with you. It's up to you whether or not you want to use them in certain computations. So if you do not use a certain predictor as an input to a computation, then it's just unused. There is no need to select or deselect anything.
Okay.
No more questions from the weather.
Anirudah, can you hear us?
I can hear you.
Fatima, the connection dropped. Wait a few minutes to see. Very well done, anyway. Great work.
Thank you.
If you had a few more months to work on this, what would you do?
So it's actually, like I mentioned, there were a few things that we didn't have time to do. For example, improving the algorithm and everything. But as a software developer, I'm trained to, if I have more time, I'll just fill it up with more and more work. So this is something that we always do. So, of course, there are always ways to make the code much better, make it more performant, make it look, make the GUI look much cleaner, improve the UX. But all of these things they need to be done over time.
It's good to see that you're so motivated.
Yeah, in fact, I plan to, since this is an open source project, I plan to continue working on this.
Oh, that's great. Very good news from us. We hope that you receive more maybe pull requests and contributions from other people that the project goes done?
Yeah, because yeah, sure, but I think for that we must publicize the project and say that this is a project that needs contributors, and these are the issues that newbies or people relatively new to these concepts can tackle. So I think if we have that, then we might as well have contributors.
So have you already identified issues?
Yeah, in fact, while working with Fatima and Tim, so I can share the screen and show you that how we used to develop on GitHub. So we have, so I just showing you the issue list that I closed 26 issues and I still have 13 issues open. So some of them can be tackled by newbies or who do not have any background on what the software is, if the issue is well explained. Yeah, so we have a bunch of issues as with any software. Yeah, some of them are low-hanging fruits, so they can be taken up by anyone.
Yeah, maybe you can label those low-hanging fruits with the help wanted, so that people that want to contribute, they know where to start from.
Sure. Yeah.
Idea. I think they are having a technical problem out in the webinar room. So my colleague Milana is gonna go and check, otherwise we'll see the webinar. So maybe somebody else from outside, some participants have further questions. There are still people connected. Apparently they couldn't hear you. So.
I think it's just with Fatima's room.
Yeah, it must be.
Apparently everyone can hear.
But we will wait a little longer, and if nothing happens. So you are working as a software developer, if I understand well?
Yeah, that's right. Yeah, in Paris. So I had no knowledge of meteorology, these things before. So the first few months are really challenging for me to understand what the hell is going on.
But you had great mentors, right?
Yeah,
so
they explained me with handwritten notes, and we almost met every week, sometimes more than once a week. So that was really